Hi, welcome to Hashtag Math. Local behavior, or behavior near the roots of real zeros, is the last piece that will enable us to graph polynomial functions. First of all, let's get an idea of how polynomial functions look like. All polynomial functions towards the end of the graph look like going to either positive infinity, like that, or negative infinity, like that, as x approaches infinity, or it would go to positive infinity as x approaches negative infinity, or it would go to negative infinity. So all polynomials end like that, and in the middle, they just wave smoothly and continuously, like this, maybe like that. That is a typical polynomial function, or something maybe like this, waving a lot and ending down there. They all look like that, waving in the middle and ending towards negative or positive infinity on both ends. Now we will analyze behavior near zeros or roots. And that is, what is our graph doing around the x-intercept? Is the graph touching or crossing the x-axis? How does the graph touches the x-axis? How does the graph crosses the x-axis? So we have all those possibilities. For example, if my graph crosses the x-axis here at -4, does it cross like a line going down, or does it cross like a line going up? If the graph crosses at 3, suppose, is the graph crossing like a cubic, or is the graph crossing like a reflected cubic? If the graph is touching the x-axis, like suppose it touches at -1, is it touching like a parabola opening up, or is it touching like a parabola opening down? That is what we have to learn. We start by stating the relationship between roots and factors of the equation. So we want to see the equation and how does the equation gets to be graphed, and vice versa. We want to see the graph and come up with an equation whose graph could be the given one. If -2 is an intercept of my graph, we call it also a real zero or a root. So suppose our graph has a root of -2, then the corresponding equation has to have a factor of x plus 2. You see, because -2 is a root of x plus 2. If 3 is a root of our polynomial, then the equation has to have a factor of x minus 3, because 3 is a root of x minus 3. If the graph of the function touches the x-axis at 0, then x has to be a factor of the equation, since 0 is a root for x. And inversely, every factor of a polynomial represents a root on the graph. If, say, x minus 2 is a factor of the polynomial, say p of x, that is, the polynomial looks like x minus 2 and then multiplied by any other factors, like, I don't know, x plus 1, whatever. If x minus 2 is a factor of our polynomial, then the root of x minus 2 is going to be 2, and that is a root of my polynomial. If x is a factor, then 0 is a root of the polynomial. So factors correspond to x values where the graph touches or crosses the x-axis. The multiplicity of a 0 or root of a polynomial is the number of times the corresponding factor appears in the polynomial. For example, for x equals 0, which corresponds to the factor x cubed, the multiplicity of 0 is 3. And the second factor, for x equals 2, the multiplicity is 2. And the last factor, for x equals 5, the multiplicity is 1, only the is not written there, is a 1. And we write the root x equals 0 has multiplicity 3, the root x equals 2 has multiplicity 2, and the root x equals 5 has multiplicity 1. Let's think about it. What's happening at 0? The corresponding factor, x, is being cubed. So there is a change in signs, going from negative to positive. Whereas at x equals 2, the corresponding factor, x minus 2, is being squared. A squared is always positive, so there's no change in signs there. So the result is, if the multiplicity is odd, then the graph crosses the x-axis. If the multiplicity is even, the graph touches the x-axis. But it is also true that if we go from the graph to the equation, when the graph crosses the x-axis, the multiplicity of the corresponding factor is going to be odd. Also, if the graph touches the x-axis, the corresponding factor of the equation has an even multiplicity. Here we have several examples to analyze the behavior near a root. So how does a graph touches the x-axis? Look at the two left graphs. So in both graphs, the behavior near 0 looks like a parabola opening up or down. The bigger the power, the flatter it looks like. From that, we can analyze the examples we have on the right. Let's look at this graph. The root is 3, and it looks like a parabola that has been shifted 3 units to the right. So the corresponding in the equation should look like x minus 3 squared. That should be a factor of the polynomial. On this graph, you see it's the same root, so the factor should be x minus 3. It looks like a parabola, but it's flatter. So I can use a 4. When you see the graph and you want to get the equation from the graph, you can approximate the exponent by looking how flat it looks near the root, but it's always an approximation. So we can say this is like x minus 3 to the 4th power. The same happens to parabolas opening down. Like this parabola opening down here, in this example, it touches at -2. So the corresponding factor has to be x plus 2. And because it looks like a parabola, would be x plus 2 squared. And since it's opening down, I'm going to write a negative sign. So this should be a factor in the equation of a graph showing that behavior. And again, in this graph, -2 is again a root. The corresponding factor is x plus 2. But because it's flattened, as we did before, we can say it's about the 4th power or a 6th power, and then a negative sign because it's opening down. That should be a factor. This graph has 3 roots. Corresponding to x, we have the root x equals 0. Corresponding to x minus 3 squared, we have the root x equals 3. Corresponding to x minus 1, we have the root x equals 1. Root x equals 0 has multiplicity 1, so it crosses. Root x equals 3 has multiplicity 2, so it touches. And root x equals 1 has multiplicity 1, so it crosses. Let's see how it touches. We're concerned now how the graph touches. So my graph is touching at the root 3 there. We have to figure out if it touches opening down or if it touches opening up. For that, we look at the sign of the remaining part of the polynomial. So what we do is we're going to plug in the root x equals 3 into the polynomial in all x's except in the x that corresponds to the factor. And that is, I am going to plug in the 3 for this x, and not in this one, not there. So we get 3 times x minus 3 squared times 3 minus 1, which is 6 times x minus 3 squared. And that tells me that the way the graph is touching the root 3, it's like a parabola opening up because the number in front of the factor is positive. So for this polynomial, the graph is touching like a parabola opening up. As we did before, now we want to know how a graph crosses the x-axis. You see, all polynomials in this graph cross the x-axis in the same way, from negatives to positives. And all polynomials in this graph, which are the reflections about the x-axis of the above polynomials, cross the x-axis in the same way, positive to negative. So let's look at the examples on the right. This example here, this is a line going up. The behavior of this on the root -3, it's like a line going up. The corresponding factor is x plus 3. That should be a factor on the equation of the polynomial. So any polynomial function whose behavior at -3 looks like a line going up should have a factor of the form x plus 3. On this graph, we have the same root. The factor is x plus 3, but now it crosses like a cubic. So we cube the factor, and then the equation should have a factor of the form x plus 3 cubed. In this graph right here, you have the same root of -3, so the factor has to be x plus 3, but as you see, it's flatter than the previous one, so it might be a power of 5. And then this graph here, the behavior around -3 is like a line going down. The factor is again x plus 3, but this time it's going down, so It's got to have a negative sign in front. In this graph, the root is -1. The corresponding factor is x plus 1. And because it crosses like a cubic that has been reflected, it has to have a power of 3 and a negative sign in the front. Any polynomial that behaves like this at -1 should have a factor of -x plus 1 cubed. This graph here again, we have -1 is the root, so the factor x plus 1 should be in the equation. It's flatter, so we can write a 5, and then again it's reflected, so we need a negative sign. Let's analyze the local behavior of p of x. The first thing is, let's establish the roots. Roots are x equals 0, x equals -3, and x equals 1. So 0, -3, and 1. Let's analyze the local behavior at -3. We know that because the corresponding term has an odd power, it crosses the x-axis. But how does it cross the x-axis? Well, we replace x by -3 in the polynomial everywhere except at its corresponding factor. So we replace it here and here, and we get -3 times x plus 3 cubed times -3 minus 1, which is going to give us 12x plus 3 cubed, which means the graph is touching the root -3 like a cubic. So it's touching like that. For x equals 1, the multiplicity is 1, so the graph is again crossing the x-axis. Let's see how does it cross the x-axis. Because it's a linear term, it's going to be like a line going up or a line going down. What we do is that we replace x equals 1 everywhere except at x minus 1. So we replace it here, and we get 1 times 1 plus 3 cubed times x minus 1, and that is 27x minus 1. So it crosses like a line going up like that, and we discard this behavior. And oops, it looks like I didn't write anything for x equals to 0. Well, let's do it. So plug in x equals 0 to know the behavior around 0 everywhere except at x. So we're going to plug it. So we plug it here, and we get x times 0 plus 3 cubed times 0 minus 1, which is -27x. So it looks like a line going down like this. Okay, now we want to find an equation of a polynomial whose graph could look like the one we are given here. Let's look at the behavior at -6. The corresponding factor is x plus 6, and because it's crossing, it should be an odd power, a line going up, so the exponent is 1 and positive in the front. The next root we encounter is 4 and is touching. The corresponding factor is x minus 4. Because it's touching, must look like a parabola, and because it's opening up, we leave it positive. What is the possible equation? Well, p of x has to have a factor of x plus 6, a factor of x minus 4 squared, and then it might be multiplied by a number. Sometimes it's easy to find the number a, sometimes it's not. Here it's going to be easy because it is clear and easy to see the y-intercept. So the graph goes through the point 0 for x and 2 for y. And if you plug in that into the polynomial that we have so far, it's going to be p of 0 is going to be 2. And if you plug in 0 there, that's a times 0 plus 6 times 0 minus 4 squared. So that's going to be a times 6 times 4 squared. Then we divide both sides by 6 times 4 squared, and a is just 1 over 48. And this is an approximation. Sometimes we can get it exact, sometimes we don't. In this case, it is exact because it's a very simple polynomial. We see that how the graph is touching the x-axis is not being flattened. So the candidate is going to be 1 over 48 times x plus 6 times x minus 4 squared. Okay, let's analyze now this big one. We have 4 roots. X equals 3, x equals -4, x equals 5, and x equals -1. Because of the multiplicity, we can see that at 3 it touches, at -4 it crosses, because it's odd. At 5 it crosses, and at -1 crosses. Let's plot in the roots. 3, -4, 5, -1. So we have to analyze how it crosses and how it touches. Let's start from the left at x equals -4. So you're going to plug in -4 everywhere in your polynomial except at the corresponding factor. So you plug it here, here, and here. So what we get is -4 minus 3 squared times x plus 4 cubed. You do times -4 times -4 minus 5 times -4 plus 1 to the 5th power. That's going to be a huge number that I don't want to calculate. And besides, I only need the sign. And I already know that it's a cubic. So it crosses like a cubic. The only thing that I need to know if it's been reflected or not. So let's look at the signs. This piece here is positive. This piece here is negative. And this piece here, it's a negative to an odd power, so it's negative. When we multiply the three signs, plus times negative, we get that this is x plus 4 cubed, and here a positive sign. That means it crosses like a cubic that has not been reflected. It crosses like that. Now we analyze how the graph crosses at -1. So at x equals -1, again, we replace -1 everywhere except at its corresponding factor. So we plug it here, here, and here. That's -1 minus 3 squared, -1 plus 4 cubed, -1 minus 5 times x plus 1 to the 5th power. Again, we are only interested in the sign. The first one being squared is always positive. The second one is positive, and the third one is negative. When we multiply the three signs, we get x plus 1 to the 5th power, and then some number here that is negative. That means this is crossing at -1 like a quintic that has been reflected around the x-axis. The only difference with the cubic reflected about the x-axis is that this is going to cross flatter around -1. So it crosses like this. Now let's analyze what happens at x equals 3. And again, we plug in 3 everywhere except here to its corresponding factor. So we plug in the 3 here, here, and here. That's going to be x minus 3 squared times 3 plus 4 cubed times 3 minus 5 times 3 plus 1 to the 5th power. Again, I'm just interested in the signs, so this is positive, this is negative, this is positive. So what we get is x minus 3 squared with a negative number in the front. That means that the behavior near 3 looks like a parabola opening down, like this. Good. And the last root we have to analyze is at x equals 5. Again, we plug in x equals 5 everywhere except at x minus 5. And so we get 5 minus 3 squared times 5 plus 4 cubed times x minus 5 times 5 plus 1 to the 5th power. This is positive, this is positive, this is positive. So we get x minus 5 with a number in front that is positive. So it crosses like a line going up, like this. And we finish analyzing the behavior near zeros of all the polynomials. In this last example, we're going to try to get the equation whose graph is the given one. So we're going from the graph to the equation. -6, corresponding factor x plus 6, 0, corresponding factor x, and 7, corresponding factor x minus 7. Let's analyze one by one. Here, at -6, you see this graph is crossing like a line going down. So we must have a factor of the form -x plus 6 in our equation. So far, we know that the polynomial we're looking for has -x plus 6 as a factor. Then we look at the root 0. The corresponding factor is x, but it's touching, and it's touching like a parabola going down. So the corresponding factor should be x squared, like a parabola, but opening down negative. The polynomial equation should have a factor of the form -x squared. Lastly, the root 7. The corresponding factor is x minus 7, and you see it crosses like a line going up, so it's positive, and x minus 7 should be a factor of my polynomial. Then this polynomial multiplied here by some kind of a, that in this case is not as easy to find. So we get x squared, x plus 6. I'm multiplying these two signs, that turns positive, x minus 7. This is an equation that approximates the graph that we were given. it's not going to be the same because the a, we would have to find it to do an exact equation. If we have enough time, we can go to a given point like this one here, -2, 4, replace p of -2 equals 4, and then solve for a. That would give us that a. Okay, so we finished analyzing all of our examples. Thank you.